This is a Research Infrastructure Services instructional video. In a previous video, we went over a bit about R and using R on the server on the RIS compute cluster. In this video, we're going to go over a little bit more in depth using R on the compute cluster and creating our own Docker image with an R package that we want to use to be able to utilize R the way we want on the RIS compute platform. So the first thing, as I've mentioned before, that we need to do is at Docker Hub, there is official images for R made by RBase. So if we go here, we can see that this is by the R group, and they have their official images and all of that. So one of the things I've mentioned before is we go to look at tags, and of course latest is usually always the tag that most people use, but in this case, when you're building an Docker image that you want to do, you may want to pick, instead of latest, you want to pick a particular version type, because some of the software may not be compatible with the latest type and all of that, but if you pick a particular version type, you will be able to secure and make sure that your software is going to work, the packages you want are going to work. And so to create a Docker image from the base of one of these R images, the first thing we need to do is create ourselves a Docker file. So in this case, I've created a folder that I've called R-example Docker, and I've created this file within it that's empty right now called Docker file. Now, the first thing you want to do is when you create a Docker file, which will eventually be compiled into our image that we'll use, is that you have to start from some form of base. Or if you're really enthusiastic and you want to install an OS yourself, you can start from there, but most times it's easiest to start from a base. Since they have bases and they have base packages already installed for R in Docker Hub, we can start with that. So the first command that we use is from, and then the name of the pack, we say from, and then a space, and then the name of the package, colon, and then the tag we want to use. So you can see here I have in my software that I'm using for editing, which is, if we go look, it's Visual Studio Code. I have Docker extension installed that it will recognize Docker file code for us. So here we can see it says from base image colon tag. And so in this case, tag, we are simply going to tag with, we're going to use the current version, which is 4.0.3, but instead of using latest, we're going to go ahead and use the tag, specific tag 4.0.3. Now the great thing about RBase that I've mentioned before is that in the images they create, the version of R is the tag number that they use for that R image. So in this case, we now have a Docker file. It says it's has from, which is telling Docker when we go ahead and compile that it's using the base, that we're using this image as our base, so from our base image 4.0.3. And so now that will use the base of our Docker image. So if we go ahead and save that, and then we go over here, we can go ahead and look at what happens when we compile that. So in this case, this example, I'm going to end up using DESeek2 to do a simple analysis. I've downloaded some expression data previously that there are links to in the documentation along with this example and this video. You can get the information there, as well as generating some phenotype data randomly so that we can do the analysis, because the only information we have on the this data is the expression data that was publicly available that we downloaded through NCBI's website. And so that when we get to that point, there will be definitely some differences between what people might get for results, but that's because we're randomly generating the phenotype data, and so that's going to have an effect on our expression and whether or not we see differences in the gene expression based on those phenotypes. So in this case, the first once we've got our base image set. So in this case, we're saying from our base 4.0.3. Now that we've got our base image set, we can use Docker to build it. So in this case, what we do is if you have Docker running locally, that's what you want to do. That's recommended is that you run Docker locally on your system. Sometimes your local system, your personal computer, may not have the requirements necessary to compile a particular image, especially if you're using a lot of you're creating a big image. And so we do have documentation, I believe there's a link for it on the page, to use Docker on the RIS Compute platform to create an image, to compile an image. But in this case, we're using it locally because this image isn't going to be big. So the first thing we want to do is run a build, Docker build. So in this case, we'll do Docker build and -t for tag. And then you'll want to give it a tag name. In this case, that tag name is your username, followed by a slash, followed by the name of the location of the doc file, what you want to name it, followed by a colon, and then the tag you want to give it. So in this case, I want to use my username slash, in this case, we're going to do our example. I do believe it's our example. Let's double check what we named it here. Our example -docker. Oop. Go back here. Our example -docker, colon. We'll just do 4.0.3 for the tag, because that's the base R that we're using. And then in this case, we want to use, then you need to tell it the directory or the folder where you've stored the Docker file. So I've stored it simply in a folder called our example Docker, which is the name of the image that I'm creating. So if I go ahead and hit enter, let's go ahead and build it for us. So step 1, it says from our base, and then it successfully builds it. And so you can see it's successfully tagged as this. Now, once you've built it, you can push it to Docker Hub so that you can use it. So Docker push, and then the name of what you gave it for a name. So in this case, if I can type, Docker 4.0.3, and it tells you that it's pushing to this repository. In this case, I've already created this Docker image so that I could write up the documentation that we did and take screenshots and all of that. So it's going to tell me that this already exists. The layer already exists, and it doesn't need to push more information that direction. So it's pushed it, and it says, you can see it's finished, and it's successfully pushed it. So what we have is a Docker image that runs off the base, our base image of R 4.0.3. And we've done nothing so far to change that. So the next step that we want to do is we want to go ahead and we want to go back to our Docker image. And a lot of times it's recommended that you put notes or along with your code that you want to do. So in this case, we're just going to say set base image from our base using R version 4.0.3, so that a comment, so that people in the future, if they look at our Docker file, if they want to know what we're doing, we've told them what we're doing with this code. We've told them essentially what this line of code does. So since we want to install DESeek2, the next thing we want to do is we want to install needed R packages. In this case, we're going to install DESeek2. So in order to do that, one of the things you want to do is you want to tell the Docker image run, and you can see here it's prompting me so what you can do with the run command. So you run code is run, and then you give it command, and then you give it parameters. So in this case, we want to run R-E, and then what we're going to tell R to run is install packages, which is an R command, DESeek2, and you want to make sure the packages you want to install, you want to make sure that you are spelling them correctly, because if you don't use the correct capitalization and all of that, it won't necessarily find the package you're looking for. So in this case, we want to tell it to install DESeek2 dependencies equals true. This is saying that yes, we want to install all the dependencies that this package relies on. And then you can also tell it the repo you want it from. In this case, http://cran. We're using cran, which is the default anyways, but this is ensuring that we use the correct place that we want to use. And in this case, you can see install packages, and then the parentheses, we have the information we need, just like if you were in R itself and you were using the install packages command. So basically, this is what this command does in the Docker images. Say run R using run R, giving it this command to run while in R, and that way then the base image that we create will now have DESeek2 run in it. So now if we save, it'll save it. We go back and we go to run it. So if we want to go back, we go to Docker build, give it the same tag, Docker example. We'll install it again, or we'll build it again. This time with the new line in there, it'll attempt to install DESeek2. So if we go ahead and build, it says so step 1 of 2 from RBase does that. Step 2 of 2 run R. So of course it goes into R. You can see it's starting up R. And then it tries to install packages. In this case, you can see that DESeek2, it says it's not available for this version of R. But the difference is what you can find out if you dig into this. So if you want to figure it out, you can do Google search to try and it's your best option when you're trying to debug is a Google search. If the R code doesn't tell you exactly what's wrong, so it's saying DESeek2 is not available for this version of R. Well, the issue that you run into in this case is like a lot of bioinformatics packages. DESeek2 is not available through CRAN. It's available through Bioconductor. It's a Bioconductor package. So what that means is if we go back to our Docker image here, what we're going to have to do is we're going to have to install the Bioconductor manager, the Bioconductor installer, so that we can install DESeek2. So instead of DESeek2 this way, if you do a Google search, you'll find that the package you need is called BioC Manager. And again, we want our dependencies to be true, and we want our repo to be the CRAN repo. This just guarantees that we have our CRAN repo. So then now we do run r-e again. In this case, now we're using BioC Manager, the package that we've just installed. And we use BioC Manager : install, and then the package. So in this case, again, DESeq2. This is what we wish to install. Go ahead and put this in single quotes here. And so now the software, the image when it compiles, when we tell it to build, it will attempt to install the BioC Manager, and then it will attempt to use the BioC Manager to install DESeq2. So we go ahead and save this again. And if we go back to our, here, we just hit the arrow up. So we go back to our build command. We can say, okay, build -t, tag, all of that. Hit enter. And now you can see if we slow it down a bit, it's pulling up R again, and it's installing packages BioC Manager. So now BioC Manager is available through CRAN. So you can see that it's going to install these packages into the local library for R so that it can retrieve them. And it's also going to install all of these dependencies that it needs. So you can go through here, scroll through as it runs. You can see it's downloading all the packages, all the packages that we need to install this. And so you can scroll through, it's doing its install here. And while a lot of this installing is in red, it doesn't mean it's bad. For some reason, R likes to use red, even though a lot of times when you're installing things, R means a warning or an error. But as you can see here, it's done. It was installing UTF-8 in this case, then it was installing pretty units. So you can scroll through and you can see done, done, done. It's installed that package, done here, done, 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 and we've seen no errors so far. So here it's installing a lot, and it'll keep going here for a while. This does take a while. So as it scrolls through, I'm not going to talk a lot. We're just going to fast forward to the point at which the next step, which we might find an error or see if it's truly installed the packages correctly. So we'll let it keep going in this case. Okay, so now that it's continuing to install, but if we look here, it says an error. So if we go here, look, we're trying to install package curl. So if we come down here, it says no package libcurl found. So it's trying to find on the base image, it's trying to find this library that's part of the operating system called libcurl, and it's not finding it. So here it's given us an error. And if we look, R a lot of times is very helpful in what you need to do to make sure you have the packages necessary to install what you want. So if we go back up here, it says configuration failed because libcurl was not found. And then it says try installing, and then it gives us a bunch of different install options, ways to install this package onto into our system, so that then R can use it to install the package that it's trying to install within R. So in this case, it gives us 3 different types of commands, and then in parentheses it tells us which operating system versions use which command. And so we can go through and figure that out here in a moment. I'll go through the steps of finding what operating system we use, so the package, the base image that we're using, uses, so that we can go ahead and use the correct install to install this library, so that then our package can install. So if we scroll down, this is still continuing. And if you look here, okay, so down here, warning, the install packages didn't happen because it couldn't find curl, and so it exited and it ended up not installing the BIOS manager. So then when we try to install here with the BIOS manager, since it's not installed correctly and there were errors in its install, it's not getting it's not installing the packages we wanted. But if you also look down here, it looks like what I mentioned previously of you need to make sure you have the syntax of the package you're trying to install correctly. In this case, it says it couldn't find DESeek2, and if you look here, that's because we spelled it incorrectly. So what we need to make sure we're installing the package correctly. So now we're going to have to go back to our Docker container. And so let's first make sure we have the correct name here. But now we're going to want to go back and we're going to want to install the library in the image we in the image the base we're working from. So in order to do that, first we need to you want to find the OS version, so you can find the version of Linux you're working on. I'm not going to directly do that command right now, but I'm going to show you the command within this. So the command you want to find out what the operating system of the image you're using is, you can start up that Docker image, run it, and then while you're interactively running within that image, you can you can type cat and then /etc/os release like this, and when you hit that, it will tell you the base OS in the version you're running. So in this case, if you run this on the base the R base Docker image, you'll find out that they use Debian as their base operating system. So in that case, we want to use the apt-get version of what it told us to do, the commands it told us to install. So if we go here, again, we want to use a comment, install library dependencies. This simply says that we're installing the library dependencies that the R packages we want to use will need. So first thing you want to do is apt-get update. So this tells apt-get to update and make sure it's the latest version. And then we'll use this / here to tell it that we're going to do a new line. So we'll tab over, and then and tells us the command we want to do. So in this case, apt-get install. You want to use -y, and then --no install recommends. And when you're installing these libraries in a Docker image, you want to use this -y and this --no install recommends, so that it installs these packages without any prompts to the user, because any prompts are not going to get a response because it's creating this image without your prompts, and it can cause errors. So now if we go back to where we were building the image and we scroll back up when we found that error, since we know that the operating system is now Debian, we can see here that Debian. So this is the package, this is the library command that we want to install. So if we copy and go back over here, we're telling it to install this library package. So then once the libraries that we want to install are all there, we'll go back here and we'll continue this command with apt-get clean. You want to clean up your install afterwards so that you can have a more compact image, because the size of the image is somewhat important. The bigger your image, the longer it takes to download it, which increases depending on how large your image, it can increase the amount of time it uses to run on compute, because it's got to download that image if that image is already in cached, and that's going to use up some of your compute time, which, while the RIS compute platform does not have any fees associated with it right now through the end of the fiscal year 2021, it will in the future, and that runtime is going to cost you. So you want to try and keep your image as small as you can make it. So in this case, we want to add the apt-get clean so that we can clean up our image. So now we've installed the dependency, the library dependency that the BIOS manager requires to be able to install. And so hopefully now when we save and we go and build, we'll be able to get rid of that error. So if we go back here, we go here. What we're going to want to do is over here, there's another option we can use before the -t, the tag part of build, that is --no no cache. And we want to use this option because if we try and rebuild it, even though our commands are similar, we have changed our commands. If you try to build it again, it will just use the cache, the Docker caches the install, so that every time you do a build, it doesn't necessarily have to do that step again. It's already registered that step, it's already got it saved. It uses the cache to not have to repeat that. But if you tell it no cache, it'll build without using that cache. And when you're debugging and you're trying to find out if things have installed correctly, you will want to use that no cache option as of the build command, so that you can see, make sure things have installed correctly. So we'll go ahead and enter here, and as you can see again, now we're running that apt-get update and the install and all that. So now we're going to sit here, and if we scroll up here, you can see it has installed the library that we wanted it to install. So now it's going to go back through that R command that we have and install that. So we'll fast forward here to the end of that step and kind of go over that at this point. And so if we take a look here, when it says installing source package curl, which is what we got that library for, it's using stage installation. We don't have that error anymore. In fact, if we look, we have an installation, and down here, done curl. It has successfully installed the curl package in the library. And so then we continue down, and it's continuing to install the different packages that are necessary. And it's still doing so. So we'll go ahead and wait here and fast forward to the when we get to the next point. Okay, so we can see here it's done. Here, down here, it's downloaded the packages. There are no errors or warnings that it says, and it's removing this intermediate container. Now we're going on to the step 404, which is the install DEC2 through the BIOS manager. And of course, you can see once again it's downloading all the dependency packages and all of that. And we'll fast forward to the point that we need again when we go ahead and look at this. Okay, so if we go ahead and take a look now that that step is finished and installing, it says it successfully built the container down here, which it technically has. But if we look up here, we have errors and that we had a lot of warnings of packages not the installation of these packages exiting with a non-zero status, which means that something happened here. And if we look up here, we have errors on dependency. Annotate is not available for gene filter, which means the dependency annotate didn't get installed properly. And again, annotate here, and then it says gene filter gene plotter for DEC2. But if we go back to the annotate, HTTR, OpenSSL, and XML have all non-zero statuses. The other three seem to be dependent on the fact that one or multiple of these packages did not install correctly. And if we go back through and we look at the errors and we scroll back up, which I'm not going to scroll through this and make you sit through me scrolling through it to find the exact errors, but if we go back and we scroll back up through, we can find that we need 2 more library packages for the OS to install. So if we now go back to here, we can give it in this install command, you can give it multiple packages to install. The 2 packages, if you were to scroll back up through all the install messages to try and locate the errors, you will find them, and it will tell us that we need to install a library called libssl-dev, as well as libxml2-dev. So now that we have those 2 put into the into our command, hopefully we'll see that all the errors will take care of themselves and the dependencies will install, and we won't get any errors when we install, because a lot of the errors that it showed were, if you scroll back through in this case, as I've done previously, you'll find that there are some dependency issues, but they all boil down to there are a couple or a few packages that won't install without these added libraries installed in the OS. So we'll go ahead and save, and then we'll go back here, and with that new Docker image, again with the no cache, because we want to make sure we can debug this Docker install, we'll go ahead and build it again. And then we're going to let it go through, and we're going to see here, we'll step through first, and we'll see that it installs the different OS libraries. So it's updating, now it's installing the first package, then it'll install the second library, and it's installed the library successfully. Now we're on to installing the R packages, which we'll fast forward through to the end to see and make sure that we've got everything installed correctly. Okay, so now that we fast forwarded to the end of this and done the install again with the new libraries, OS libraries that we put into our Docker file to be part of the image, we can see down here that DEseek seems to install the download. There's no errors. It says download packages are here. Then it says, so it mentions old packages. There's some old packages that are part of this, which isn't a big deal at all. It's just saying, hey, these were old packages, just so you know. But we have no more errors, which means our install is now correct. So now we have a Docker image that runs R 4.0.3 that has DEseek 2 installed. And now that we have a proper build, we can go ahead, and if we go back up here, again, we'll use the Docker push, and we'll go ahead and push this to Docker Hub. So we'll go ahead and do the push command. It's going to tell me preparing, waiting. It'll do the push. It's pushing some new images because some new layers, because we didn't, when we had pushed the previous image, it didn't have those layers anymore. And so this may take a little bit, as it does, the image does take up a little bit of space because we're installing some R packages and we had to install some libraries. And so we just got to wait for it to finish the push here, which can take a little bit depending. Let it process. And since it's pushed those 3 layers, all the other layers already exist there, and it gives us the digest here, and it's successfully pushed. So now if we go back to Docker Hub here, I don't know if my sign in is available on this. Yes, I can sign in as myself here. And I go to my profile, I should be able to find my packages. So here, ln rfw, our example Docker, we can go to tags, and we can see this image is now available to be used with the tag 4.0.3 because that's the version of R we used. And so if we go here, we can copy this so that we can use this on the compute platform, on the RIS compute platform. So now if we go over back to here, we're going to head and clear this out. And now we can SSH. We'll go compute 1. We'll just use client 2 in this case. Hopefully I typed everything correctly. It sure looks like it. Type in my password. And we're on the compute cluster. So now we can run this image. We've created it. It's a Docker Hub. We can access it. We can now run this image just like we do any other thing. So if we can do an export for the LSF Docker volumes. In this case, equals want storage 1, fs1. Ooh, a bit of lag there. Give it a moment to catch back up. Hopefully it catches back up here. There it goes. Inactive. So I'm just giving it my storage location here as we have in the past. So we'll do that, and then we'll go ahead and bsub dash interactive. We want to look at it dash group. So I need a group because I'm part of multiple groups in this case. Q general interactive because we're doing interactive in the future here. This interactive will go away, and the way to, as I mentioned before, the way to do the interactive will be with the dash I, capital I, lowercase s, and then Q will just simply be general if you're using general queue, or the name of your queue if you have a personal queue. So we've got those, then we'll go dash A, Docker, and then as always in the parentheses, again, the username slash name of the Docker image, colon the tag, and we've copied this directly from Docker Hub, which you can always copy from for whatever image you're using, whether it's one you've created or one that you found on there. You can go ahead and copy in that pull directory. If you copy that name like that, then when you use it on the server, you'll go ahead and be able to recognize that command. The compute platform will recognize that with its Docker system and be able to pull that for you. In this case, the command we're going to use is bin bash so that we can go into an interactive session with this image. So as long as I've made sure I've typed everything correctly here, we'll go ahead and get the job started up. As you can see, it's launched. It's pulling the image because this image isn't in cache. You see it's not too terribly large, just a little bit bigger in a couple of spots, but it's not too terribly large. Doesn't take too long to get through this pull. And now here we can see exec 204. We are now within this image. So if we do a couple of things here, we can go over a couple of things. So first is we can do the R command, which we're going to want to do here. So we'll do R, and you look, it takes us into R. And we have our version 4.0.3, which is the base image that we used, that we said we did. So that's got the correct version of R. And now if we do library to go ahead and pull in the deseek2 library, and we type deseek2, it'll go ahead and load the library for us. It'll go through a bunch of things here, and it'll pull in any of the dependencies it needs, and it'll load them. So now that we've loaded the library, we can go ahead and do session info, and we can see the information about the session. Again, R 4.0.3 running under Debian new /Linux here. And we can see a bunch of different things, but if we go down here, attach packages, we have deseek2 version 1.30.0. So we have deseek2 installed, and if we want to go ahead and check it out, we could use some of the deseek2 commands, but we'll go into that here more in a bit depth after we've worked on making sure we have the appropriate commands for R to do our DE-seek2 analysis, which we will be setting up here in a moment. All right. So now that we have our Docker image created, all the bugs worked out of it, we've pushed it to our own Docker Hub account so that we can use it. We now can go onto the server and utilize that Docker image to do analysis. So the first thing you want to do, you're not going to see it here because I've already done it, is connect to compute with the SSH command through an SSH client, whether you're in Mac or Linux, which would be terminal, or if you're using Windows, so you've got MOBA Xterm or PuTTY that you've decided to use. We log on to the server, and before we get started into the analysis, for this example at least, and sometimes depending on the data you want, you do have to do some data manipulation for R to recognize, potentially you can read in the file correctly in the way that you want. So the first, there we go. The first thing we do is ls. I'll just show you here the data file that I have. So it's GSE 1000 series matrix, and if we do a head of this, let's just look at the first 20 lines. You can see that there's a bunch of header information. It's useful if you want to know the metadata and the different things about where this data set came from. But in terms of what R needs, all of these header lines that they exist are unnecessary for R to read in and to use, and it's just kind of a bit of erroneous data in a sense. So how can we solve this? Well, the one thing we can look at is the beginning of these lines. You can see that there's the exclamation point here. So one of the things you can do in Linux is a command called grep, and then the -v option means ignore everything with the what I'm gonna, like, the matching string that I'm going to give you. So in this case, we want to use it's going to take a moment, slash there to escape, because we're using the exclamation point, which is a recognized symbol that is used for some of the programming stuff. So you have to escape it out so that it knows to look for it. Then we do our GSE 1000 series matrix, and then we'll put it into a file called GSE. It will add a little extra here called fixed. So now if we go ahead and do the head 20 of this fixed file, we can see now that we've gotten rid of all that header, and we just have a single header row that has the ID ref of the gene, the first sample, second sample, all the way on down, and then we have the counts for that gene for all the different samples all the way down, and there's a lot of genes. So now we've got our fixed file, we can go ahead and go into R. So the first thing we want to do is connect to our Docker image. Usually you want to do an export LSF Docker volumes equals your path to your storage if you want to use your storage and all that. I have that set up so that I don't have to type that every time. So we're going to go ahead and do our bsub command to get into our Docker image so that we can go ahead and use R. In my case, I've already established my LSF Docker volumes, so I don't have to type that. But if you haven't, you can do the export LSF Docker volumes equals quote your path to your storage, colon, the name you want to give it in the Docker image, end quote. So we'll go ahead and do the bsub command, bsub dash capital I lowercase s because we're going to do interactive, dash g because I'm part of multiple groups, so I need to do, and for my case I'm doing compute RIS. In the case of a workshop, you'll use the compute dash workshop that we'll set up, the queue, general, interactive. So we want the interactive queue. As I've mentioned multiple times in videos, in the future we're changing this so that that queue will only be general and the interactive portion will simply be that dash capital I lowercase s, and you won't have to worry about the different queues. Dash A, the Docker, and then the location where I stored it or saved it on my Docker hub. So you can see lnrfw is my username, / r example docker colon, and then the tag I gave it. So we've got all that. And then the final bit, the final step here is to go ahead and type that /bin/bash that we want to type, to tell it basically enter into this Docker in the bash so that we have an interactive command, interactive session going with this Docker image. This particular analysis doesn't take a lot for what I'm doing. It's just an example. So I've gone ahead and gone with the default and didn't increase memory or RAM, but you can increase memory or RAM if you need to be able to use what you want. You can also put the examples in a Docker, or not a Docker, an R file, an R script file. Once you've worked up what your analysis is, you can put it in an R script file, and then you can run that through just the normal general queue without being interactive, so that you don't have to sit there and interact with it, and still can give it the amount of memory and everything you want. So now we're in the Docker image. You can see I'm in my storage there. I'm gonna go ahead and copy that quick because I want that for my working directory within R. So go ahead and start up R. And you see start R, we got the prompt. So the first thing I want to do is going to set my working directory with set wd parentheses quote R example. That's where this is all stored. And there, I've set my working directory. Now there's a couple of libraries we want to load to be able to do some of the analysis that we're going to do later on. The first one is deseek2, which is what we're going to use for analysis, which is what we spent all that time creating that Docker image to have in it. So of course it'll load up everything here for us, get everything going. And then the next one is a package called stringer. Don't need to do anything extra to load to make sure this one's installed. I do believe it's installed as base, but we need to still load that up. So now we've got our packages that we want to use loaded into libraries so that we can access them. The first thing we want to do is we want to load in our data. So usually, at least for myself when I'm using R, I like to call my data so that I know what I'm working with, and then the arrow to tell it we're sending the command we're about to give to data. In this case, I'm going to read and delimit, and then GSE 1000 series matrix, and then fixed.txt, the name of the file. In this case, header equals true. That file we created has that header that we want to wanted to include, so we got to go ahead and load that up and tell it that yes, we want that header. And then this last one is important here, of separator equals, and then /t, because we want to escape that t, meaning tab, because that file is tab delimited. And then closing parentheses, and we hit enter. Depending on your data size, ours isn't particularly large in this case. The larger your data set, the longer it'll take to read that in. You noticed it didn't quite immediately go, which means it was loading that data set in, but we have loaded it in. So now if we want to go ahead and look, we can do head data, and we can see, cool, we have the ID, ref, GSM, we got all the names. We have that first column is the name of the gene, and we got those counts in there. So we've loaded that data, as we could see in the file previously, into R at this point. But now we kind of want to manipulate our data just a little bit so that we can use it better for analysis. So one of the things we want to do is we want to give it the row names. In this case, we're going to give the row names the names of the gene. That's this, the simplest method to this. So if we do this, what we're saying is the row names of data, our data set, is equal to data : 1, that first column. So we're saying instead of 1, 2, 3, 4, 5, 6, you can see here, that's going to be these identifiers. And so we hit enter. And now if we do that head on data, give it a moment, it's kind of lagging a little bit, I think. Yeah. There we go. We can see our row names now have the names of that gene. Well, we no longer need that ID column, so we can remove it. So if we do this, we can say data, and now, and previously we referred to it as : 1, we say : -1, i.e. we don't want that first column, or comma, sorry, not colon, comma -1, because we don't want that first column, and this is saying take out that first column. So if we hit enter, and now if we look at it, we can see that that column is gone, and we have the names as the gene names for the row names. So we've kept those gene names, they're still there, we can still reference them, they're just outside of the column, so they're not going to get confused when we try to do some of the counting and all of that. So one of the things we need to, that DE-seq is going to need in the future is it needs even numbers, it needs integer numbers. So we've got to get rid of all of those digits, all those numbers after the digits, and we need to round them. So one of the things we can do is data, again with that arrow, because we're replacing it, is round, and then we're rounding data, and we want digits equal to 0. We don't want any digits, we just want that integer. We don't want it, so we do that, use that round because we want the integer, and we don't want any digits after that integer. So now if we go ahead and do the head on our data again, we can see we've got nice round numbers, and you can see it's done. So here we have 363.9, it's rounding appropriately how we expect it to. Now, so now we've got our count data in, and we have that all ready to go, so we can do our analysis, because this is DE-seq2, this is differential expression analysis for usually RNA-seq is what you're looking at. You can use the software to do similar type things with other data if you so wish, but it's really designed for RNA-seq expression analysis. But in this particular case, we don't have any phenotype data for this expression data. What we can do is we can go ahead and generate random phenotype data. So the first thing we want to do is we want to create a matrix that we're going to use for our phenotype data. So we need, let's see how many samples we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 samples, so we want a column, a matrix that's 10 by 4. We're going to give it 4 phenotype phenotypes to go off of, and we're just, for the sake of simplicity, we're going to call them group, treatment, disease, weight. And so the first thing we need to do is we need to create that matrix. So I'm going to call it pheno.data. Then we're going to use the arrow and as data frame, because we want this as a data frame, but we got to generate it as a matrix. We're going to say matrix. And in this case, we want to repeat a repeat of zeros 4 times, 10 times. So we're going to repeat and then repeat. So in this parentheses, we're going to repeat 0 4 times, and then we're going to repeat this 10 times to fill our matrix. And then the number of rows we have is going to equal 10 because we got the 10 samples, and then the number of columns we've got is equal to 4. And then I do believe that's one more. That should be what all we need. Let me double check here quick. I gotta scroll on my screen. Yep, so we hit enter, and now if we go pheno.data, we can see, yep, we got the 4 columns and we've got 10 rows. So the next thing we want to do is we want to go ahead and fill in this data, and we're going to do it randomly. But we also want to name, give it, so we have V1, V2, V3, V4, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we don't want those. So one of the things we're going to do is change the names of those. So the first thing we have to do is we have row names. Again, we're using that row names, and we want the we're going to say of pheno data. We're going to set those row names to the column names of data. And using this, instead of trying to type out all those different names and maybe messing them up, what we're doing is we're making sure those identifiers are the same. So now we do that. No errors there. And next we want the column names. So column names of pheno.data. With the arrow again. And we're going to call them, we're going to actually give it the command, the C, so the grouping, the list here of group, as I said, group, treatment, disease, and weight. Oop. Of course, I need to use type correctly. So now we have those. So now if we type pheno.data, we can see we have all of those names as the row names, and we have group, treatment, disease, weight as the column names. Now that we've got that set up, we're going to want to put in the phenotype data. So the first thing we're doing is we're going to fill out the first row of group. And this one's going to be fairly simple. So group pheno data in the square bracket, comma 1. So that first column, we're going to tell it to give us this list of repeat 1 5 times, and then repeat 2 5 times. So now we're gonna, what that's gonna do is it's gonna go put into this matrix 1 5 times. So those first 5 samples are gonna have a group of 1, and then the next 5 samples are gonna have a group of 2. So the next thing we want to do is give it a treatment. And so now we're going to have a little bit of a different form for the treatment, because so that we have group 1 and group 2 now to simulate, data from a research project that we would want. In each of those groups, we're going to have the 2 treatments that we're going to arbitrarily set up. And so if we go pheno.data square bracket comma 2, this will set up that second column with the treatments. So what we're going to do is basically we're going to say in each group that treatment is what we're going to do is we're going to set up the treatment as 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2 through the different groups. So now to do that, we do that list again, and then we do repeat. And in this case, we're repeating another list of 1, 2. So we're repeating 1, 2. And we're going, since that's 2 numbers and we have 10 symbols, we're going to repeat that 5 times. So now if we hit enter here, we can, we'll go ahead and do a check of our data quick to see the last 2 things we did. So pheno.data again, you can see that group we have 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, and then on that treatment we're going 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So now the next thing we want to do is we want to create a disease state of 1 or 2. And the way we're going to do that is we're going to use this a random generator that we have. So to do that, we're going to do the following. We're going to, again, we want to set here we go. We want to set pheno. Oh, no, it doesn't want to seem to respond. There we go. Pheno.data square bracket comma 3. So that third column, again with the arrow. And now we want to give it this list again of, we want to round because this number doesn't do any give us round numbers, but we want actual 1 or 2 round, and then absolute because this this normal generation that we create is going to create negative and positive around a mean. So in this case we're going to say R norm. We want 10 of them. We want a mean of 0.5 and a standard deviation of 0.15, which will give us, through some trial and error, I know that this will give us values around 0 or between -2 and 2. And what we can do then with that absolute, it gives them all from values from actually this might be 1. So we have a disease state of 0 and 1, meaning 0 typically meaning no disease, 1 meaning disease. And then so from 0 to 1, and then we want digits, because we're doing that round again, equal to 0. We don't want any digits in it because we want those as counts. We want that 0 or that 1. So now if we look at our pheno data, we can see that we have 0s and 1s there. So, and it's random because each generation of this disease state is going to be random. And so when you run it, you might not get the same number of diseased and non-diseased animals. That's just how that's going to work, because we're, like I said, we're doing random generation. So now we need to fill in our weight data. So again, we do the pheno.data square bracket comma 4. and then we do the arrow, and in this case, again, we're going to do C, and then round, and we don't need absolute value this time because we're going to be doing a positive value. Our mean is going to be a lot higher, so we're not going to hit that negative. So we're going to do just without that absolute, we're going to go into the R norm. And again, we need 10 numbers. Our mean this time we're going to say is 175. So our mean weight around these randomly generated numbers is 175 kilos, pounds. It doesn't really matter in this case. We're simply representing something. That's a large value, and then standard deviation we want to say is 25 pounds. We want there to be a bit of differentiation here between the weights to try and kind of simulate what could happen in a real study or in real life, and as well as give us a bit of differences so that we can hopefully get so that DE-seq can hopefully find some differentially expressed genes for us, because since we're randomly generating here our phenotype data, we might or we might not have the different differentiation because we're randomly generating it. So in this case, then again, we're rounding. We want digits equal to 0. We want these weights. We don't want any decimal points in these weights. So if we hit enter, and now we take a look at our data, pheno.data, we can see we've got a bunch of weights there. So we have like 167, 120, 215, 180, 197, 171, 110. So we've got a bit of range there, which is good. So the next thing we need to do is we need to look at we need to change some of these phenotype data information to factor. We need to tell it to be a factor for doing this, because it's a factor. It's not like random, like it's not numbers, it's factors, because we've got two different states. So the first one is we need to go click on it here, pheno.data, and then if we do $group, so this is saying that particular column of this data frame, the group column, we need to use that arrow, and then we simply say factor. Oops, if I can type right, factor. And then we type again pheno.data $group, and then the levels we want it to have is C, and then we want to put these in the double quotes so that it knows that these are strings and not otherwise. So this is saying that this particular vector of this data frame is a factor in its levels are 1 and 2, which is what we've given it. So then we go ahead and hit enter, and then we need to do this again for treatment and disease. So pheno.data $treatment, and then the arrow again, and then just the same again, except we obviously have a different name. So treatment here, and then the levels in this case again are going to be 1 and 2. So we put those in like that, and now the for disease, it's just a little bit of a difference. Again, pheno.data $disease, the arrow, factor, pheno.data $disease, and then levels in this case, again with the C, but this time there's 0 and 1, because that's the disease state that we've given it, is 0 representing no disease, 1 representing disease, which is generally equivalent of what people use when it comes to research. yours may differ, but that's what we're going with in this case. So now those are set as factors. So now with all of that, we want to set up our DESeq2 object. And so to do that, I'm going to call it DESeq2.data. This is going to be our data object of that. And so we're going to go seek data set from matrix, because we have a matrix. We're setting up this matrix. We're going to use our data, and then the next thing is our phenotype data, which we've generated, but we have, and now we need our model. So in this, the tilde, if you're using DESeq2, you want this is how the model type goes. We want tilde group plus treatment. Let's see what all we have here. Again, in the model, I gotta look at my list here. So okay, so we're putting everything in the model, which is what we want to do. So wait. So now we have everything in that model. We hit enter. Yep. It's kind of telling us something that's not really that important. We've already switched things to factors. For some reason, it also wants, I think, weight. It's like, this is a factor too, and it's not really a factor. We don't have enough data points, I think, for it to not realize that it's not a factor. So now we have this DESeq2 object. Now we want to run the analysis. So I'm going to call it simply going to call it DDS. Too many D's. There we go. DDS. And we want this stored as an object so that we can reference it. Then we're going to simply run DESeq on our DESeq2.data here. As soon as it loads, there we go. A little bit of lag there. Sometimes happens depending on your connection. But all right, so we're running the DESeq command on our DESeq2.data that we've generated. So now we do that. It's going to say it's estimating size factors, estimating dispersions, doing gene-wise dispersion estimates, mean dispersion relationship, final dispersion estimates, fitting model and testing. It's going to do all this analysis for us. And so it ran. The more data you have, the larger your data size, the longer this step's going to take. We don't have too terribly large amounts of data in this case. It's just an example of using, in this particular case, DESeq2 as an example of doing some analysis with R. So what we want to get is our results. So in this case, I'm going to call them res for results. We tell the results command, and then we say DDS. Now this is going to store all the results from that analysis into this object for us to easily retrieve here in a little bit when we get to that point. The next thing I want to do is I want a list of all the genes. So in this case, the genes are simply the row names of our data set. So we set that. So now if I do head genes, we can see, yeah, there's the list. And you can see the first, so many of it. First 6 it looks like, but we've got a list of all those gene names. And so one of the things that we have that's part of this results is different columns. So now if we do head this res, we can see we have this base mean, this log 2 fold change, this LFCSE value, a stat, a p-value, and a p-adjusted. So we want to take a look, just for the sake of our analysis here, our example, we want to take a look at that p-value, and we're going to say we want anything that's less than 0.01 for a p-value. So what we can do now is we can say significant dot genes, we'll create another object here, is genes, and then we want out of those that vector of genes we've created, we want which So you use which. In this case, it's and what which does is it gives you the ones that meet the requirement that you're going to say. So in this case, we want our res p-value to be less than 0.01. And so what this is going to give us is it's going to give us a list of genes that have this p-value of less than 1. Because where this res.p-value, since this is a vector and we have this list of genes, which is the same list and same order as this genes we created, any point in time where this p-value is less than 1, it gives us the identifying number, which will be the same as the one in genes, so it'll give us the gene name for any gene that's got that p-value of less than 0.01. So now we do that, and we can, if we do a head, I don't know how many there's going to be in here, but if we do a head significant.genes, now I can't guarantee that there's going to be any significant genes since we're randomly generating the phenotype data, but if we do a head, we got 6. We have at least 6 genes, so there's probably more. So if you really want to know, you can do length and then significant.genes. And in this case, we have 25 significant genes. 25 genes that, because of that expression value of the data that we downloaded, are randomly generated phenotype data. It says that these genes are most likely significantly different. There's a significant different expression value in these genes based off this phenotype data. And so now we have that list of genes, but we want to do some more with the actual data itself. So one of the things we can do is we can say sig.data, arrow is the data, and then we want which, because we're doing rows here, we want which, and then again that res $p-value, because we want that p-value less than 0.01, and then comma, and then close the square bracket. So we want those we want our significant data of those rows of data from our data file where that p-value is less than 0.01. So we just want the significant data, the genes that are significant, because we're going to do a little bit more beyond just this analysis of which genes were differentially expressed. We're going to kind of do some k-means clustering on these genes to see what they are. See if we can see any clustering based off these or whatever. Just kind of an example. The first thing we're going to do then is we're going to create this significant data set. Now we want to do some k-means clustering, but we need to do this k-means clustering, we need to transpose that this significant data set. So to do that, I'm going to name another object t.sig.data for transposed, and then the arrow, and then we still want it as a data frame, so we got to tell it data frame because otherwise it's going to transpose it as a matrix, and we don't want that. So then t for transpose, sig.data, and then close that out there. And so if we do head of sig.data, you can see here we've got it that way. And then if we do head of t.sig.data, you can see we've changed things. So now we have the rows are the samples and the columns are the genes, and that's we're kind of how we want to do this to make sure that we're good on the k-means clustering that we're going to do. It has to be this direction. So the next thing we want to do is, I do believe I have in the example on the website that the row names, we want to give the row names and the column names the correct row names and column names. However, if you look, we already have correct row names and column names. We don't necessarily need to do that step. It's possible you might have to. That's why it's included in the example. As we can see here, we don't need to in this particular case, so I'm not going to do that. I'm going to move into the next step that we want to do, which is the actual k-means clustering. So the first one I want to do is fit 2. So basically, I want to cluster these into 2 groups. Just see. Randomly, is it important that these are into 2 groups? So k-means, this is for the k-means clustering, t.sig.data, comma 2. So what we're doing is we're going to do this k-means clustering based on 2. It doesn't take too long to do this step. At all. And then what we want to do is we want to create a thing called compare data. So we want to cluster this up. So we want to compare this data and we want to look at things. So if we do compare.data, we're just creating a data frame here to look at this clustering, to see if these 2 clusters, if we can cluster them significantly on anything. So what we want in this data frame is we want our pheno.data, we want the group here, then we want pheno.data, we want the treatment, then we want the disease, so again pheno.data $disease. And then the final one is what we want from that k-means clustering. So in this case, we want fit2, and it's called fit2 simply because, fit2, oh, there it goes. Okay, fit2, it's called fit2. I called it fit2 simply because we were clustering through the k-means cluster on 2. We're clustering 2 clusters. So now we've got this data frame. We can go ahead and let's look at this. Let's look at this data frame. It's not too large, so we can look at the whole thing. So if we do compare.data, we see we have our group, our treatment, disease. None of that's changed, but now we have that fit.2. And if we look, we can see that there is some clustering, and we have a 1 or a 2. Is clustered it into 1 or 2 groups. And if we kind of try and look, you can look across and see, is there any combination of things, whether it's group and treatment, or disease and treatment, at all, that kind of fits this cluster, and see are these clustering off of any of our data that we've got there. And it looks like for the most part kind of not really clustering off of anything in particular necessarily. Because you can see here we've got this group 2, and we've got disease and non-disease, we've got treatment 1 and treatment 2, and then we go down here, we've got 2 more, but we've got 2 diseased, treatment 1 and treatment 2 again, and now we're in the second group. So that doesn't seem to be clustering off of any of those states in any form. And then we can see we have diseased and non-diseased in group 1 as well, and we have treatments 1 and 2 in group 1, and we have our group in the first cluster, and then we have groups 1 and 2 in that first cluster as well. So it doesn't look like necessarily it's significant, but we're not seeing any clustering based off this information. We're just these particular genes were significantly expressed differentially. And so the next thing we want to do is, okay, well, maybe not 2, but what if we go with 4? What if we cluster on 4? Maybe there's a difference. So then we can do k-means again. Again, t.sig.data, we want that transposed data for this, 4. Instead of the 2, we're doing 4. So we hit enter, and now we do a similar thing. So compare.data 2, we'll call it 2 so that we have a different one, the arrow. And then data.frame, we want it as a data frame. Pheno.data, $group, pheno.data, $treatment, pheno.data, $disease, and then fit for $cluster, hit enter. Oop, I'm mistyped somewhere. Yep, if we go back up here, you can see I accidentally hit an E in my pheno when I was typing. Happens sometimes. Make sure, you just want to make sure everything's spelled correctly. So now if we hit enter, yeah, we're good. Just one of the perils, of programming or using R, any sort of language. So now if we go ahead and look at compare.data2, we can see we do have different groups. We have 1, 2, 3, and 4. And if it looks kind of like, nah, there's not really grouping anything based off of these groups, which in this particular case isn't necessarily surprising. We're running the seek2 analysis on only 10 samples. Yes, we have a lot of genes, but only 10 samples. And we're running this cluster off of those same 10 samples, and now we're down to 25 genes because we wanted to see if those significant genes could tell us anything about the group, and it doesn't look like they're doing anything. But like I said, we're low on sample size, so the number of samples, and we also randomly generated this phenotype data. So just because we found some significantly differently expressed genes based off of our criteria that we use doesn't necessarily mean they mean anything, because this is just an example. We're just looking at using R and doing some analysis with R and being able to utilize the RIS compute platform to do this R analysis. So now we want to take some of this information outside of R. We want to get it out of R. And one of the ways we can do that is we can do this some writing. We can write out to a file, and we can also, while I don't have a graphics connection to the compute cluster here, I can still output graphs to a PDF file that I want. But the first thing we're going to do is we want that list of significant genes. So what we're going to say is we're going to write, because we want to write this out to a file, we want the data significant.genes. So we want that data within that vector that we have of significant genes, and we want to output it to a file called significant.genes.txt. It's just going to be a text file of a list of these significant genes that we've discovered. So if we hit that, it's going to write that out for us, and we'll look at that here in a little bit once we get back out of R, but I don't want to look at those files until we've done the bar plots and the graphs as well. So one of the things we can do is we can create a bar plot. So what you want to do, and to do this you need to initiate a PDF. So we say PDF, and then we're going to call this gene1.pdf. This is just going to be the first gene. We want to change the height. I did some manipulation. I did some looking, so like to generate these graphs, and we kind of want to change some of the height and the margins and stuff on these graphs just to be able to fit everything how we want it. So in this case, I'm going to do a height of 10, and then I want to change the parameters of the graph. So we want these margins, and I want them to be 11, 4, 4, and 4. In this particular case, to get these graphs correctly, you might have to mess with these yourself and find out which ones will work for the graph that you're generating to display it appropriately within the PDF. So in this case, I want those parameters that way. So now I'm going to create a bar plot of that significant data. So what I'm going to say is bar plot, and then what we're going to use is t.sig.data, and we're going to use that first column. We're going to say main, which is the name of it, and we're going to say these are gene1 counts, and then the names.arg that we want is the row names of t.sig.data. And let's see, is there anything else we want to put in here? And then we want to change the LAS option, just to make this look a little bit different. We're LAS equals 2, those row names, we're going to turn them sideways so that they fit better. We're going to want to have them fit better. So then we come back here, we hit enter, and now it's generated our bar plot into the PDF, and we say dev.off, do you believe, like this. When we say that, we're telling it that we don't want any more output to go to that PDF file. So dev.off, null device, 1. Yeah. So hopefully that should be okay. We should have generated that graph. Now that's just the first gene. We wanted it to do the first gene. So the question is, well, what if I have a lot of significant genes? In this particular case, I only had 25, but what if I have 500? And what if I wanted to create these bar plots for all 500? How can I do that without, you know, a lot of changing things? So one of the things we can do is you can use a for loop in R. So we're going to do a for loop here. So we say for, and then we have I in 1 colon, and then we want that length. We want how many significant genes there are. So we say the length of that significant genes. And then here. So now we've got a continuing thing here of that's what that plus means. So in this, we're going to do that PDF. So we want to start that PDF. The name we want to give it is, we want to paste. And then string, this is where that stringer comes into place. We want string replace all. So the problem with the names of these genes and using it this way is that the names of these genes might have weird non-alphanumeric symbols in them. So this is how we're going to replace those. So we want to string replace all, and what we're going to use our significant .genes to name this file, and we're doing it I. So since we're looping through, this will be the first one. So this file will have the name of that that gene in it, is what we're doing here. And so what we want to replace is we want to use a regular expression here of //w plus and basically this will replace any of those erroneous characters that we don't want, non-alphanumeric, that we don't want in these files, with underscores. So sometimes maybe there's already underscores in those names, which you can see there are some places where there's underscores, but there's also slashes and different things. As you can see up here, we have this slash. We don't want that when we're naming a file. That's going to mess things up. So what we're going to do, what this is doing, is this is replacing all those other non-alphanumeric points with that underscore. And so now we have the name of the gene as the base, and so we have that comma dot PDF. So it's going to be that name of that gene dot PDF. That's going to be the name of our file. Here we're going to separator, tell it the separator we want between those two strings that we're putting together is nothing. We don't want any space there. And then again, height equals 10. So we're telling it we want that height to equal 10 in this case, which again, as I said, was a testing I had done. So that's that was some trial and error to try and find what looks right. So then again, we want that parameter and those margins equal to 11, 4, 4, and 4. Oop. You can see this plus is continuing because this is all going within that for loop. So now onto the meat of what we're doing besides starting that PDF is we want to bar plot this. So in this case, t.sig.data I. So we want I. Oop. We want column I. So we want the column that's associated with that gene. Main equals, and then we're going to paste again here, which is combining strings together. So we're going to paste significant dot genes I, because again we're using I, we want that counts, and then our separator is going to be a space in this case. We want that space. We want that separation because this is the title. We want that separation in the name in this case for our title. So we're going to continue here, and then again our names.arg is equal to row names of I do believe it's, if I look here, row names of that t.sig.data, and then we want to change that LAS equals to 2. We want to change that to the 2, so I'll change that information to 2 there, and let's see, that's the end of that line. And then we want to tell it dev.off again, and then close that out. It might, depending on how many genes you have, this might take a little bit. We close out that for loop, it looped through, and we should have all those files. Hopefully this ran correctly and we didn't mess anything up, and I didn't mistype. But now we've gone through, you've seen that for loop, we've done our analysis, we've got all these output files. Let's go look at those output files and make sure they are what we want. So let's quit out of R. I don't want to save my workspace image in this case. So now let's look, ls, and hey, look, we have significant genes.txt, and then a list of we have all these PDFs of the different gene names that we found, as well as that gene1.pdf. That was just an example of showing you how to do a bar plot and getting it output to PDF before we went into the for loop to do all those genes. So now we have all this information. So now if I do a cat on that significant genes file, you can see that's a list of all the significant genes, and those are all going to match up here to all the PDFs we have, because we made sure to do this, you know, programmatically, so that we don't mess up any of the names and we don't have to go through and do it get all this information ourselves. So, and all of these commands now that we've gone through, you can easily wrap these all up into an R script and then run that R script in the background using this this Docker image that we were utilizing to do this. So with all that there, I can't display a PDF via the SSH, but I'm going to go ahead and go into my example here, and let me connect via an SMB mount so that I can get this onto my local computer here. There we go. All right. So now we have those pulled up. What I'm going to do is, let's see if that PDF comes up. All right. I'm going to bring this over onto the screen so you can see it, and we're going to take a look. So it's a little bit big for the size that I want to show, because I don't want to go beyond my screen here, because I kind of want to keep everything the same size. But we can see here that we've got this name of the gene.pdf, and then we have that gene name and then counts, and then we can see it's a bar graph to the counts for each down, and then if we go down here, each individual sample. And we've, like I said, we've turned with that LAS equals 2, we've turned that those names on their side, so it's a lot easier, so that each one is with that bar graph. It's really easy to see. We don't need to worry about it. And yes, the graph's a little bit tall, but we need to do that to be able to include these turn on their side sample names in the as the bottom part here, so that we can better visualize it. So that's what part of the trial and error is when it comes to creating graphs in R. You kind of have to sometimes mess around a little bit and look up options. Like I said, as I've said in other videos, as I mentioned before, Google is your friend when you're trying to find answers to using some of these programming languages or software. At RIS, we will try to help you as best we can if you have questions, but when it comes to particular software, we don't necessarily have expertise in that software. We do have some expertise in some softwares, like myself. I am relatively experienced with R as well as a couple other languages, so that if there are questions, I might be able to help, but we can't guarantee that. So like I said, Google is your friend, but again, that's using R and the custom Docker image we created with the packages we wanted on the RIS compute server. So if I wanted to, all of those commands I gave, like I said, I could put them in an R script, and then I can run that in the background with that Docker image I created, just the normal in the general queue, non-interactive, or run the command of R script and then the name of the R script I give, and it'll give me the same results, or the same output of PDFs of these bar graphs of the counts for the genes that are significant, whatever number those happen to be based off of the random phenotype information we put in, as well as the list of significant genes. Now, like I mentioned it before, I want to mention it again with this example. If you're following along with this example, your significant genes in your phenotype data when it comes to the disease and the weight are going to be different because it's randomly generated. I've designed this example to randomly generate that information. So depending on what numbers are generated for both of those phenotypes, your significant genes are going to change. I have done this example multiple times, just testing and running this example for both creating the documentation as well as this video, and I've gotten a difference of 10 genes to over 500 genes. So it's just dependent on that randomly generated phenotype information. And it's different because, one, random generation of phenotype information. Two, we don't have that many samples, so there's some errors and potential errors introduced in having a low number of samples. But all that said, that is using R with the RIS compute platform. We started with generating our own Docker image based off of R-base image that we created. We added our own packages into it that we wanted to use, as well as had to adjust some of the libraries and install some of the libraries that were needed for those packages to be installed. And then once we had that Docker image all set up and actually compiling correctly, we pushed it to Docker Hub, and then we went on to the compute cluster, and we pulled that image and used it to do our analysis using that package that we installed.